Okay, hello MathCounts friends. Yesterday they released the chapter tests from this year. And so I took a look back at our results from the chapter and tried to identify some of the difficult problems, problems that a lot of us, got wrong. And so this is a little histogram here that shows on the sprint the problems that were difficult. This is how many of our top 7 students missed the problem. So these ones were really difficult, but really we did really well overall. So I wanted to go over some of the hard problems. And please pause the video when I get to a problem that you think you may have missed, and go ahead and try to solve it. So let's see. So we'll go to this one here. So this one says, what is the value of the expression shown? Express your answer as a common fraction. And it's a very big, ugly thing that can look a little overwhelming. The key here is to start with the innermost part here. So this is just 5/8, right? So that's 5/8. And when you add 1 to 5/8, you get 13/8. So if I look at now, let's see, if I look at this part here, that is 13/8, right? And then if I do 3 over 13/8, what I can do is take the reciprocal of this and put the 8 up here and the 13 down here. So now I have 3 times 8 is 24. Let's do that in another color here. This is 24 over 13, which is all of this part here. Well, it's all of this originally. Here is 24 over 13. You add 1 to that, so you have to add 13 on the numerator, sorry. So now we have 37 over 13. So this whole thing, let's grab another color, I guess. This whole thing here is 37 over 13. 37 over 13. And now we can put the 13 up here and the 37 down here. So this is 2 times 13 is 26. So let's grab another color. 26. Oh, that's not a good color. Oops. 26 over 37 is this part. And now we do 1 plus that, so we have to add 37 here. And that becomes, what, 63, I believe? So let's grab another color. 63 over 37 is all of this. And then now it's just 1 over that, which is 37 over 63. And yeah, I forgot to put the, let me just pause the recording and check that answer. Okay, yeah, that's correct. 37 over 63. All right, let's take a look here. Let's go on to the next one. So this says Alva adds up all the positive integers less than 2023, so not including 2023. And Beth adds up all the even positive integers also less than 2023. What is the remainder when the absolute difference between those two sums is divided by 1,000? So what is the difference between those two sums? Well, the difference is going to be what you get when you add up all the odd integers that are less than 2023. So that's 1 plus 3 plus 5 plus, and then dot, 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 plus, all the way up to 2021, because 2023 we're not including. So this is the absolute difference when you take Alva's sum and subtract Beth's sum, take the absolute value. You get this. So what is this? Well, we have a trick to add up sequences. You can take the starting value in an arithmetic sequence, and you can add the ending value in an arithmetic sequence, and you can divide by 2 to get the average value of all the numbers in the sequence, and then you can just multiply by the number of numbers in the sequence. So we can do that here. The starting plus the ending is 2022. We divide that by 2, and then we multiply by the number of numbers in the sequence. Well, how many numbers are there in this sequence? Well, we've got 1 out of each pair. So if you took 1, 2, you would take just the odd one. 3, 4, you would just take the odd one. 5, 6, you would just take the odd one. So we've got 1 of each pair all the way from 1 up to 2022. So that's also going to be 2022 divided by 2. So we're going to multiply this by 2022 divided by 2. And of course that's 1011 times 1011. Now we need to find the remainder when you divide this by 1,000. I think one easy way to think about this, one little trick here, you could multiply this out, but this is a sprint round. You don't have a calculator and it would give you a big number. But you could do that. It's not too bad. But one way to think about it is you've got 1,000 plus 11. And you've also got 1,000 over here plus 11. And if you do FOIL on this, you're going to get first. That's going to be divisible by 1,000. Outside, that's also going to be divisible by 1,000. Inside, that's also going to be divisible by 1,000. So only this, the last ones, 11 times 11, is the part that's not going to be divisible by 1,000. So it's just 11 times 11 is 121 is the answer to that one. All right. Let's go to the next one here. So again, feel free to pause the video and take a look here before you look at the solution. This one says Aaron draws a regular hexagon, and then Becca connects the midpoints. Okay, so these midpoints here of the sides of Aaron's hexagon. So this bigger one was Aaron's hexagon to form another regular hexagon. So that's the smaller one. As shown, what is the ratio of the area of Becca's hexagon to the area of Aaron's hexagon? Express your answer as a common fraction. So it's a little tricky to compute the area of a hexagon. It's easier to compute the area of a triangle. And so let's break each hexagon down into 6 triangles. So for example, this here would be one of the triangles on the bigger hexagon. And on the smaller hexagon, we could take a look at this triangle here. I didn't draw that very straight, but you get the idea. And if we could find the ratio of these two triangle areas, that would be the same as the ratio of the two hexagon areas, because each one of these triangles is 1/6 of the area of the hexagon that it's part of. So let's see if we can find the ratio of the areas of these two triangles. Now, we obviously can't find the absolute areas because they didn't give us any side lengths or anything. So let's just call one of these edges 1. And I think it might be easier to call this bigger one 1. So let's say, yeah, I probably should have done that in the other color, huh? So let's call this blue triangle side length 1. And then what is the side length of the other triangle going to be? Well, what you can notice is that this distance here from the center out to here is actually the altitude of the bigger triangle. And it's the same length as the side length of the smaller triangle. And so what is that distance? Well, here we have a 30, 60, 90 triangle. We know that because a regular hexagon can be split into equilateral triangles, and half of an equilateral triangle is going to give you 30 degrees here, 60 degrees here, and a right angle here. So the altitude of this triangle is, if you know your special right triangles, the ratio of the sides is 2, 1, square root of 3. Or if this is 1, this is square root of 3 over 2. So this altitude over here is going to be square root 3 over 2. And what that means is that this distance here is also going to be square root 3 over 2. So, so now we know the ratio of the side lengths of the triangles. It's just square root 3 over 2. And one cool thing is that if you have similar figures and you know the ratio of some corresponding part, some corresponding one-dimensional part, you can just square that ratio to get the ratio of the areas. So for example, if I had a star, well, maybe I won't draw it as, but if I had some weird shaped figure, let's say like this, and I had another weird shaped figure that was similar to it, and I knew that the ratio of this side, you know, this side here to this side here was 3/2, then I could just say, okay, the ratio of the areas is 3/2 squared. So I'm going to use that same trick here. The ratio here of the side lengths is square root 3 over 2. So I just need to take that square root 3 over 2 and square it, and that gives me 3/2. Now, since that's bigger than 1, that'll be the ratio of the bigger one to the smaller one. What did they want to know? They want to know the ratio of Becca's hexagon to the area of Aaron's hexagon. Becca's was the smaller one, so we're going to have to do 2/3 for this one then, right? Okay, which, let's see, which problem was this? One sec. Okay, this was 22, I believe. Oh no, we did, no, 22. Oh, I'm sorry, it's not 3/2, it's 3/4. Ah, okay. Yeah, wow, that was bad. Okay, I've got to square this. That's going to equal 3/4, which is less than 1. And so that is what they're asking for. They were asking for the ratio of Becca's hexagon to Aaron's hexagon. My apologies for that one. Trying to think about too many things at once here. All right. Okay, great. So let's go up to this one. So this one says, what is the sum of all positive solutions? I believe this is problem 26. And you guys did great on 24 and 25, so I'm just skipping those ones. What is the sum of all positive solutions to this thing? Now this is much bigger than just a quadratic, because what we're usually used to is dealing with quadratics and maybe cubics. This is a big polynomial here, and this one is also a big polynomial. This one's a cubic. This one, how many x's does it have? 1, 2, 3, 4, 5. This is like a 5th order polynomial here, and this is a 3rd order polynomial over here. But let's write it all out and see what we can do. So x minus 1, and let's factor this out. So x squared plus x minus 2, that's going to be x plus 2 times x minus 1, if I'm not mistaken. Yeah, because 2x minus x is going to be x, and then 2 times minus 1 is going to give you -2. All right, and let's factor this one out as well. So this one is x, let's see, this is going to be a negative, so let's see, it's going to be a -2 and a -3, I guess. So x minus 2 times x minus 3. And that's going to equal everything on this other side. So here we have 12 times, let's see if we can factor this one as well. So -4, and we have a +3, so that's going to be -3 and -1, I guess, right? So x minus 3 and x minus 1. And then this is going to be x plus 2. All right, that's great. So let's take a look here. One thing we can do is start to cancel out a few things. Now, this is kind of a trick of this problem, is that when you cancel something, so for example, when you cancel out this x minus 1, this x minus 1, you have to remember that -1 is one of the roots of both sides. In other words, if x is 1, then this side is going to be 0 because it's 0 times all this stuff. And this side is also going to be 0 because it's 0 times all this stuff. So one of the solutions to this equation is 1. And you have to make note of that before you cancel these, because you might lose that information when you cancel these out. So let's write the solutions up here. We just want the positive solutions, and we want the sum of all those. So let's keep track of the positive solutions up here, PS. So one of them is 1. And I'll put a comma in case we get some more. So these are the positive solutions. So one of them is 1. We've canceled that one out now. Okay, we can also cancel out this x plus 2. That'll give us a solution of -2. But we don't care about the negative solution. So I'm just going to cancel that out and not write anything up here. The next one we can cancel out is x minus 3. So that gives us a positive solution of 3. And now we have managed to cancel all the x's on this side, and we just have x minus 1 times x minus 2 equals 12. I think the best way to solve this is to make a quadratic formula out of this. So let's go back to, let's expand this out, I guess. So we get x squared minus 3x plus 2. That's the product of these two, and that's equal to 12. I want to have a quadratic form, so I'm going to subtract 12. That gives me x squared minus 3x minus 10 equals 0. And let's see, can I factor this one out? I'm going to have, let's see, a 2 and a 5. So if I do x minus 5, because I want this thing to be negative, and then x plus 2, that's going to equal 0. So this gives me two more solutions, -2, which is not a positive solution, and 5, which is a positive solution. So now we have 1, 3, and 5. They wanted to know the sum of all positive solutions, so we just add these three numbers together and we get 9 for our final answer. 9. Okay, great. That was a tricky one for sure. All right, let's see. So this one says, Edward, oh, this one was a tough one. And these last four problems, no one got right, except for this one. I think that Gavin got this question right, so congratulations to Gavin. This one says, Edward has a meeting at 4 o'clock p.m. Yeah, so again, this is problem 27. Edward has a meeting at 4 p.m. He leaves his house at a random time between 3 o'clock and 3:30. Okay, so let's make a timeline here. This is 3 o'clock, and let's put every 15 minutes. So we've got 3:30 here. So somewhere in here is when he leaves. So somewhere in here is where he leaves. And then it says, due to traffic, it takes him a random length of time between 30 and 45 minutes to get to the meeting from his house. Okay, this is really kind of an interesting one. We've got two different random things together. Now, I'm going to assume that it's uniformly random in between these two. In other words, it's no more likely that he'll leave at one time than another time. So let's take a look. It's going to take him a random time between 30 and 45 minutes to get to the meeting from his house. Now, let's say he starts at 3 o'clock. When are all the possible times that he could arrive? That's the earliest. In that case, between 30 and 45 minutes, he's going to arrive. So if we start here, and you add on another 30 minutes, you're going to get to here. And if you add on 45 minutes, you're going to get to here. So these are all the possible times he can arrive if he actually leaves right at the very beginning of that time. Okay, let's consider the other case. Let's consider the case where he leaves exactly at the end of that time. So right at the end of that time is 3:30, and we add 30 to 45 minutes on to 3:30. Let me just draw these. Let's see, I've got to draw my 15-minute increments here. So this is 3:45, this is 4 o'clock, this is 4:15, 4 o'clock here. All right, where was I? Yeah. Oh, I probably should have read the whole problem before I got going here. It says, what is the probability that Edward arrives early? So he's supposed to arrive by 4 o'clock. That's the magic time. And what is the probability that he arrives early? So we want to know the probability that he arrives before 4 o'clock. Express your answer as a common fraction. Okay, so if he leaves at 3 o'clock, he's definitely going to arrive early. We know that. In fact, let's do this problem since I already started it. So let's say he leaves at the very end of that range, right? So if he leaves at the end of that range, it takes him 30 minutes. So that's this point here. If he leaves at that time, we add 30 minutes, we get to here. We add 45 minutes, we get to here. So this is the range of times he can arrive if he leaves at the end. So if I take any, so we did 3 o'clock starting time, and we did 3:30 starting time, and everything else is going to be somewhere in between, right? So maybe I'll just make a whole bunch of similar lines like this. You know, if I started a minute later, it would be something like this, and there would be another one like this. And actually, how many of these are there? It's infinite number of these, right? So it's because it's not like he has to leave exactly at a particular minute. And actually, I'm not really drawing that very well because it should be more tilted. It should be sort of filling in this parallelogram, I guess. So let's draw it like that. If he leaves at 3:01, it'd be like this, 3:02, and so on, and everywhere in between. So I'm filling in this whole parallelogram with all the possibilities of when he can arrive, I guess, if that makes sense. So you might think, oh, he's going to arrive sometime between 3:30 and 4:15, and so the probability that he arrives early is 2/3, because 2/3 of that time is before 4 o'clock. But that's actually wrong, because if you look at this parallelogram, there is a higher chance that he will arrive in this 15-minute bracket than there is that he will arrive in either of these two. And actually, this parallelogram could be split into 4 congruent triangles. just like this. So you've got this part here is got a certain probability based on the area of that, and then this part here has another probability, and then this part here has another probability, and then this part here has another probability. So that's one way to solve this, is to think about the area of this parallelogram, and you can see that 3 of these congruent triangles are arriving early and 1 is arriving late. What's the probability that they'll be on time? Probability that they'll be exactly on time, exactly 4 o'clock, I guess in a mathematical sense, is 0. You never arrive exactly at a particular time because time is a continuous variable. So 3/4 probability that they'll arrive early, 1/4 probability that they'll arrive late. That's one way to do this. Another way to do this would be to say, maybe think about all these different starting times and think about what is the probability for each of these. I guess that's another way to think of it. So so if you leave at this time, the probability that you'll be early is 1, right? Because we said that you're going to arrive sometime in this range, which is all early. And the same thing for all these points in the first half of the time that he can leave. So all these, you're basically averaging a bunch of 1s, 1, 1, 1, 1, 1 for all these starting times, right? And then for these starting times here, at the very beginning, the probability is 1, but by the time you get to the end, it's 0. So in other words, if he leaves at 3:30, he's going to be late, guaranteed. Or he's not going to be early, at least, guaranteed, because it's taken half an hour to get there, and the earliest he can arrive is 4 o'clock. So there's a probability 0. So all this time, the probability is 1 that he'll be early, and by the time you get to the end here, the probability is 0, and it's going to change linearly between that. So yeah, you can say, what is the average probability here? The average probability is 1/2. So then you have to take the average of these 2 probabilities, because it's equally likely that he's going to start in the first 15 minutes as that he's going to start in the second 15 minutes. So it's probability 1 and probability 1/2. You average those 2, you get 3/4, which is the same answer we got by looking at the area of this parallelogram and splitting it into 4 triangles. So that was that one, a very tricky one. Only Gavin got that one, so big congratulations to Gavin on that one. It's a very tricky problem because the probability of arriving at any time within this range is actually like a trapezoid. You can actually think of, so if you look at the height of this parallelogram, it ramps up linearly, and then it stays the same all the way through here, and then it ramps down linearly. So you've really you could think about it as a trapezoid instead of a parallelogram if you want. It's the same thing. You've got 4 congruent triangles, and 3 of them are early and 1 of them is late. All right, let's take a look at the next problem. So this one says, what is the least 9-digit positive integer that contains each of the digits from 1 to 9 exactly once and is divisible by 99? Okay, so first of all, in order to be divisible by 99, that means you have to be divisible by 9 and you have to be divisible by 11. So this is going to test whether you remember your divisibility rules. The number 9 one is pretty easy. You just add up all the digits and see if it divides by 9. And if you add up the digits from 1 to 9, let's see, that's going to be 1 plus 9 divided by 2 times 5. So that's just going to be equal to, did I do that wrong? I did that wrong. 1 plus 9 divided by 2. 1 plus 9 divided by 2 times 9. Yeah, because you do the first plus the last divided by 2 times the number of them. So you got 10 over 2 is 5 times 9 is 45. So the sum of all the numbers is 45, which is divisible by 9. So we don't even have to check this. No matter how you arrange the numbers, it's going to be divisible by 9. So then you have to ask yourself, is it divisible by 11? And yeah, that you kind of just have to know there's a trick to finding out if a number is divisible by 11. What you can do is you can write down all the digits. So for example, let's just do 121 since that's an easy example. We know divides by 11. What you do is you take all the odd digits and you add them up. Okay, so you add those up, you're going to get 2. And then you take the even digits and you add them up. So in that case, you also get 2. And then you subtract these 2 results, and if it's divisible by 11, then the whole original number was divisible by 11. So what we need to do is when we're ordering these 9 digits to get a positive integer, we have to make sure that the odd numbered ones add up to something that is different from what the even numbered ones add up to by 11 or 22 or 33 or something like that, or 0. So let's take a look at that. So I'm going to write the 9 spots, and actually I think I'm going to write them sort of alternating. So you got the odd digits up there and the even digits down here, just so that we can more easily see what we're adding up. So this is my 9-digit integer. I'm just writing the lines, the spaces where the digits go like this. So if we were trying to make the smallest 9-digit positive integer that we could make, we would just say, oh, let's do 1, 2, 3, 4, 5, 6, 7, 8, 9. And if this is divisible by 11, we know that's going to be the answer. So let's just check that. So we add up the top digits. So we've got 4 plus 5 is 9, plus 7 is 16, and 9 is what, 25? So this is 25 up here. And then you've got, well, you've got 12 plus 8, this is 20 down here. So those, if you subtract that, you get 5, which is not divisible by 11. So that means that 1, 2, 3, 4, 5, 6, 7, 8, 9 is not divisible by 11. Okay, so now we have to kind of rearrange some of the numbers to get this difference to be divisible by 11. Let's think about what we want to get that difference to be. So I'm going to call, let's call those two sums big S. I don't want to use little s. Okay, let's just do s and t. And let's say that s is the bigger one. So s minus t is going to be a positive number, or 0, I guess, if they're the same. So we could have s minus t equals 0. That's one possibility. Or we could have s minus t equal 11. Or we could have s minus t equal 22. Or we could have s minus t equal 33. We can't go up to 44 because there's only 45 total. We're not going to have 45 and 1 because we've got more than one number that we're adding up here. So let's just consider these. So let's start with s minus t equals 0. That means s and t are the same. And since they add up to 45, we know that both of those sums have to be 22.5. Well, there's no way you're going to get 22.5 by adding up a bunch of integers. So we can cancel that one out. And then if we want to get s minus t equal 11, what we're going to have to do is from that 22.5, we're going to have to make s 5.5 bigger than that and t 5.5 smaller than that. So 22.5 plus 5.5, that's going to get us up to 28. So let me see, let's write that here. So we've got, this will have to be 28. And 5.5 less than 22.5 is going to be what, 17? So 28 minus 17 will give us 11, and 28 plus 17 will give us 45. So that's what they're going to have to be if we want to get it to 11. Now, s minus t equal 22, we're going to have to add another 5.5 to s, which is going to give us something that's not an integer. So that one's impossible. And then if we add another 5.5, so that's like taking 28 and adding 11. That's, did I do this right? Let's see, 28 plus 11 will be 39. Yep, 39. And then 17 minus 11 will be 6. So 39 minus 6 does indeed give us 33, and 39 plus 6 does indeed give us 45. So is it possible that we could have the digits sum to these numbers? And no, it's not, because 6 is too small. We can't add up. I mean, we have at least 4 numbers in each of these sums, and if we take the 4 smallest ones, 1, 2, 3, 4, that already adds up to 10. So this is not going to work either. So altogether we have, we know that the sums have to be, sums have to be 28 and 17. Okay, and I'm going to say, I'm going to just guess, it's pretty educated guess, that this is the 28 one up here, and this is the 17 one down here. Well, I guess if I tried to make 28 out of 4 numbers, could I do that? I probably could, by taking some of the biggest numbers, but I don't think that's going to be a good strategy, because I want a small number here, for example. So I'm gonna just say that 28 and 17 go like this. This is 28 and this is 17. So now I just have to figure out ways to arrange these numbers so that I get a sum of 28 on top and a sum of 17 on the bottom, but I also have to make sure that it's the smallest numbered way to do that. So if I want a small number, I'm definitely going to want to start with a 1, I think. And if possible, I'd also like to start with a 2 and a 3, and if possible a 4 too. You know, maybe, I mean, I'm going to have to change some of these because otherwise I'm going to still have 25 equals 20, but let's see if I can start with 1, 2, 3, 4, 5. So if I start with 1, 2, 3, 4, 5, What am I going to need left in these two spots, or in these two spots? Well, let's see. This one's got 6, and we need to get up to 17, so we need 11 more. And there's no way to get 11 by adding 2 of these. So that's going to be impossible. I'm going to just say that this one can't be, it can't be 1, 2, 3, 4, 5. Can I do 1, 2, 3, 4? Well, let's see. 2 plus 4 is 6. I'm going to need 11 more again. So, but now I do have 11 because I've got 5 and 6. So let's say I put 5 and 6 down here somewhere. In fact, I want them in that order because I want the number to be as small as possible. So let's go ahead and just put 5 here and 6 here. And then the others should add up to the other thing, because we already know they all add up to 45. So what's left? 7, 8, and 9, I guess. So I've got 7, 8, and 9 that I have to put in these spots, and 9 I'm going to want to put at the end. 7 I'm going to want to put here, and 8 here. So my number in the end is 1, 2, 3, 4, 7, 5, 8, 6, 9. And that was, in fact, the answer. Quite a big answer. Usually MathCounts answers are not that big, but anyway, there you go. This answer, there it is in the answer key. So, all right, let's take a look at the next one. So this one says Stephanie rolls 3 standard dice. This was problem 29, if I'm not mistaken. Stephanie rolls 3 standard dice. What is the probability that the product of the 3 numbers she rolled is not a multiple of 8? Express your answer as a common fraction. Okay, so I like to try to simplify problems to make them a little easier when they're really tricky like this, and see if I can solve the easier problem, and maybe that gives me a hint as to how to solve the harder problem. So what if you rolled 2 standard dice, maybe, for example? So if you rolled 2 standard dice and you wanted to get a multiple of 8, I guess both of the numbers you rolled would have to be even, but not only that, one of them would have to be 4. At least one of them would have to be 4. You could have both of them be 4, because 16 is divisible by 8. So I guess what we're realizing is we need 3 factors of 2, right? And so an even number will give you 1 factor of 2, but if you roll a 4, that'll give you 2 factors of 2. So after you roll each dice, you're going to have a certain number of factors of 2. So you start out with a product. Before you roll any dice, you have a product of 1. After you roll 1 die, you're going to have either 1, 3, or 5. If you roll an odd number, that'll give you no factors of 2. Or you'll have 1 factor of 2 if you roll not a 4, a 2, or a 6. That'll give you 1 factor of 2. So so this one will be an odd number. This one will be an even number. And if you roll a 4, then you'll get up to 2 factors of 2. This is going to be a multiple of, so this is a multiple of 1, this is a multiple of 2, this is a multiple of 4, right? So I'm just going to do it that way. So I'm going to make a tree, basically, like this. Maybe I'm going to erase that E and that O, because I don't need that anymore now that I have the 2 over there. E and O, okay. All right, so we've got something like this. Now, that's after I roll 1 die. And then we're going to have factors of 8 here as well. So factors of 8. 8. So after I roll another die, let me do that one in a different color, I guess. So let's do this one. So I can go like this, and like this. Or I can go like this, whoops, like this, whoops, like this, or like this. And then if I started here, I can go like this, like this. I could actually end up with something that's a multiple of 16 if I roll a 4 and then a 4. Okay, so those are the possibilities there. And then we got one more die, so let's go ahead and grab some more colors. So here we can go from here to here, or we can go up to here, or we can go up to here, depending on what we roll. And then with the next one, we can go over to here, or we can go up to here, or we can go up to here. And then with this one, here. And there's more we could do, but these ones are already multiples of 8, so I'm not going to worry about those ones, because no matter what no matter what I roll, if I start in one of these two spots, I'm already a multiple of 8. Whatever I roll, it's going to still be a multiple of 8. Okay, so let's now take a look at how do we get to, we've got basically a threshold here, right? If we end up above this line, you know, up here, then we're going to be a multiple of 8. And there's even a spot up above, a couple of spots up higher. So I could go up here like this. But anywhere up there is going to be a multiple of 8. So I just need to worry about, the question asks that it's not a multiple of 8. So that means it's going to end up here, or here, or here. So that how many different ways, how many different paths can I take to get to these? So in order to get to this bottom one where I have an odd number, I'm going to have to get an odd times an odd times an odd. So the probability of that is going to be 1/2 times 1/2 times 1/2 equals 1/8. Now, what about to get here? This one's a little bit more tricky. I could go over, over, up, or I could go over, up, over, or I could go up, over, over. Basically, I'm going to have to go over twice and up once, where over means odd and up means either 2 or 6. I'm not talking about way up. Or maybe I'll call this one way up, the one that gets a 4. So it's over, over, up. So all those three are equally likely. So let's just figure out 3 times that probability. So going over is half, and going over again is another half, so I need to multiply by half. And going up is a third, right? Because 2 out of 6 is a third. So I guess this third is going to cancel with the 3, and I'm just going to get a 1/4 chance of ending up here. Okay, now, this is the trickiest one. What about trying to end up here? There are lots of ways to get there, because I can either go over, up, up, and any combination of those where I go over once and up twice, or I can go over twice, over, over, and then way up. And again, there's all 3 combinations of that, where the way up can be either first, second, or third. So here I've got 3 times, let's see, over, up, up is going to be 1/2 times 1/3 times 1/3. So that's over, up, up. And over, way up is, we're going to have 3 of these as well, is going to be 1/2 times 1/2. And way up is, you have to roll a 4 to get way up, so that's 1/6 probability. So this is over, way up. W. Okay. That's cool. W, up, up. So now we just need to add these all up. So we've got an 1/8, we've got a 4th. This one is going to be, we can cancel this 3 with a 1/3, and we got a 1/6 here. And then this one, we can cancel the 3. This becomes half, so this is going to be 1/8 here. So now we'll find the common denominator with all these 4 fractions before we add them up. The common denominator is going to be 24. So how many 24ths do I have for each of these? So this is 3 24ths, this is 6 24ths, this is 3 24ths, and this is 4 24ths. So I add those all up. 4 plus 3 is 7, and this is 9. 9 plus 7 is 16. 16 24ths. Yeah, so 16 24ths is almost the answer. We need to put that as a common fraction. So if we do that, we get 2/3, which is our final answer. Yeah, that one was pretty tricky. There is a little bit easier way to do it, I would say, if you happen to think about it this way. You can basically say, all right, let's, instead of figuring out the probability that we're not divisible by 3, you can say, let's figure out the probability that we, or sorry, not divisible by 8. You can say, let's figure out the probability that we are divisible by 8. So in order to be divisible by 8, there's really only 2 possibilities. You either need to have even, even, even for your 3 numbers, and any number of those could be 4s. could be any type of even. As long as there's 3 evens, that will get you there. Or you need to have an odd, let's see, an even, and a 4. This one has to be odd because if this one's even, it's already handled in this case. So basically there's 2 ways to get something divisible by 8. And we can just compute the probability of each of these and add them up, and that will give us a probability that it is divisible by 8. And then we can just do 1 minus that. So even is going to, we did that before, well no, we did odd. But even is going to be the same as odd. It's going to be 1/2 cubed, which is equal to 1/8. And then odd, even 4, the probability there is going to be probability of getting an odd is a half, probability of getting even is a half, probability of getting a 4 is a 1/6. And the thing is, these can happen in any order. So how many different ways can I order this odd, this even, and this 4? Actually, I guess this can also be a 4 too, right? So maybe that's a little tricky. Because if that's a 4, then you can't order them in different orders. So maybe that's not a good way to do it. Maybe what we should do is say odd, and then a 2 or a 6, and then a 4, and then we'll also consider odd 4, 4. We'll have those as two separate possibilities. So let's say odd 2, 6, 4. That would be 1/2 times 1/3 times 1/6, and those can be in any order. So that gives us 6 times that because there are 6 different orders. So that will altogether give us a 1/6. And then this odd 4, 4, that's going to be a probability of 1/2 times 1/6 times 1/6 because that's the probability of odd 4 and 4. And then we have to multiply that by 3 because there's 3 different orders there. And that's going to give us, let's see, 1/24th? 1/24th, I guess. Is that right? Okay. So now how many 24ths do we have? Let's write down how many 24ths we have. We have 1 24th, we have 4 24ths, and we have 3 24ths. Altogether, that gives us 8 24ths, which is equal to 1/3. And remember that this is the probability that we did get something divisible by 8. So we have to do 1 minus that to get our final answer, which is 2/3. Unfortunately, we got the same answer, which is the correct answer, 2/3 for this problem. Okay, excellent. Let's go on to the last one. This one was extremely difficult. This one was problem 30. I think they like to have at least one problem that they figure is like almost impossible, so that if someone gets it, oops, what did I do wrong here? Oh, I know, I still have my eraser on, I think. Maybe? No? Oh, I'm not on the right layer. Maybe. I was locked. Okay, there we go. All right. This is problem 30. They want to have one that's extremely difficult so that it's very unlikely that anyone will get it. So that way, if someone does get it, they don't want anyone to get a perfect score, or have it very likely that someone gets a perfect score, so that if someone does, they'll be a clear winner. So this says circle O has radius 6 centimeters. So let's draw maybe one of these radiuses to one of these points here. That's 6. And point A, that's over here, lies outside circle O, and the rays within point A are tangent to circle O at points C and D. Okay, so points C and D. These are tangent points between these two rays and the circle. Similarly, point B lies outside circle O, and the rays within point B are tangent to circle O at points E and F. So these are the 2 tangent points to these rays. And it says the measure of angle CAD and the measure of angle EBF are 60 degrees. So those are these 2 angles here. They have them labeled for you. That's nice. And it says the measure of angle AOB is 90 degrees. They've drawn that in with this right angle here. And they say, what is the area of the quadrilateral, the shaded quadrilateral here, CEDF? So that's this thing here. So this is a very hard problem. And in fact, not something that I think I've taught you enough to be able to solve. but I'll teach you how you can do it. The easiest way to do this is with trigonometry, but MathCounts problems are always possible to be done without trigonometry because it's a middle school competition. So I'll show you how to do it without trigonometry, but really in order to do it without trigonometry, you have to know a very obscure fact. So I'm going to start by drawing the radiuses from O to all of these points, F, D, E, and C, the corners of this quadrilateral. They're going to be like this. Like this, okay. So the first thing we can do is we can say that this is a right angle here, that between this AD and this radius, because anytime you have a tangent line, it's always perpendicular to the radius. And the same is true here between at this angle between this radius and this tangent line. And so what you can do is you can say, oh look, this angle, I guess we can imagine what would happen if I rotated A. I kept the A at the same distance from O, but I rotated it until the tangent point D was actually here. How much would I have to rotate it to get that tangent point to go there? Well, I guess I would have to have I would have to rotate it 30 degrees because let's see if I can, because this is currently a 90-degree angle, and I would need it to be a 60-degree angle in order to have its tangent be there. How can I show that? Because it would now be perpendicular here, and there's a 60-degree angle. There would be a 60-degree angle here. A would end up being over here somewhere, and this is 60 degrees, and well, let's see, I didn't draw that. Oh, but this would be yeah, and so what that means is that this angle here is 30 degrees, and that means that this angle here is also 30 degrees, and that means that this angle in here is 30 degrees. And now I can draw another radius that bisects this triangle here, and that means that this one is now 15 degrees. So I know that's very tiny. Let's see, but let me show you what I mean. There's an angle here that's 15 degrees, and there's another angle here that's 15 degrees. So I have two right triangles here that are, if I draw them bigger, I'm going to have, which one is a right angle? Oh yeah, let's see, let me draw that a little differently. This is going to be the right angle here, and the other one is going to be like this. Whoops, not very good at drawing this. Right angle here. These are going to be 15, these are going to be 75, and these are going to be 90. So we have a 15, 75, 90 triangle. Now, we've learned some special right triangles. We learned 45, 45, 90, and we've learned 30, 60, 90. And we've learned the ratio of the legs, or the ratio of the sides of these two special right triangles. And really what that is kind of the beginning of trigonometry, the ratio of those sides. And but I guess there are some other right triangles that could be considered special, and this one is one of them. And if you were a really eager MathCounts student, you might learn some of these other special right triangles and the ratios of the legs. And in order to solve this problem, you really have to have done that if you don't know trigonometry. You have to have memorized the ratio of the legs of this triangle. And it turns out that for a 15, 75, 90 triangle, the ratio of the legs is as follows. So the short leg is square root of 6 minus square root of 2, or no, is that right? Yeah, I think so. And then this one is square root of 6 plus square root of 2, and this one is 4. So that's That's the ratio that you would have had to memorize to solve this problem. But now what you can do is you can say, okay, look, the longer leg on each of these triangles is a radius. Okay, so that's this one here. It's a radius of this circle, and we know the radius is 6. Okay, so this is just the ratio of the lengths, but the actual length of the of that leg is going to be 6. So this one is 6, and then we'd have to multiply by 4 over this to get this leg, and this over this to get that leg. But yeah, we know that this radius here is 6. I think we had labeled that at the beginning right here. So that's 6. And this one, of course, is also 6. And not only that, but this one is 6 as well. And it turns out that if we draw a line here, we can get 2 more triangles here and here that are also right triangles, and they're also 15 degrees, so 1575, and they're let's see, did I do that right? Is it the I'm sorry, the hypotenuse. Let's see. Oh, I'm sorry, I drew these triangles wrong. These triangles were not supposed to go all the way to this point. They're supposed to stop here, so that they make up the area of the trapezoid. So not going all the way out to that intersection point, but just going out to the edge of the thing. So actually the right angles are actually here in the middle. So I drew this wrong. If you zoom in, I should have ended it here. So the right angles are in the middle. And what that means is that the 6 is actually not the longer leg. The 6 is actually the hypotenuse. So this is the length of the hypotenuse. And this one, the hypotenuse, is also 6. So not only are these similar triangles, they're congruent triangles. So we've got 4 of these congruent triangles. And what's interesting is that this length of the base of the trapezoid, DE, is actually 2 times the shorter leg of the triangle. And this other base of the trapezoid, FC, is 2 times the longer leg. Okay, so we're going to have to multiply these things by 3 halves, because to get from 4 to 6, we multiply by 3 halves. So this is going to be 3 halves of that for that distance, and this one is going to be 3 halves of that for that distance. And then, so the 2 bases of the trapezoids are the longer base is going to be twice this length, which is just going to be 3 root 6 plus root 2. So that's going to be one base of the trapezoid. The other base is going to be twice this, which is going to be 3 root 6 minus root 2. And to find the area of a trapezoid, you need to find the average base times the height, right? So 1/2 base 1 plus base 2 times the height. This 1/2 base 1 plus base 2 is just the average base. So what's the average base? These are the 2 bases. The average base, we can just add them. When we add them, these 2 parts are going to cancel out, and then we divide by 2. We're just going to get 3 times the square root of 6. So that's the average base. So if we take that and we multiply by the height of this trapezoid, which is here, we'll get the area. So we need to multiply by the height. What's the height? Well, the height, it turns out, is the longer leg plus the shorter leg. So we just have to add this 3 halves root 6 minus root 2 plus 3 halves root 6 plus root 2. And again, the root 2 parts are going to cancel out, and we're going to get 3 halves root 6 plus 3 halves root 6, which is just going to be root 6. No, 3 root 6, I'm sorry. Did I do that right? 3 halves, yeah, 3 root 6. So that's going to be the h. And now we just get 9 times 6. 9 times 6 is 54. 54 was the answer. All right, so that one was a really tricky one, but I hope you enjoyed the video. I hope you learned something, and I'm going to make another video going over the target problems, so stay tuned. All right, thanks.